My name is Erwin Reisner. I'm Professor of Energy and Sustainability in the Yusuf Hamid Department of Chemistry. I look after the chemical and catalysis aspects, and in my team is Dr. Virgil Andre, a research fellow at St. John's College, and Dr. Motia Rahman, also a research associate at St. John's College and a Marie Curie fellow in the Department of Chemistry. We develop technologies to convert solar energy into renewable fuels. Specifically, we build solar panels that can harvest sunlight to produce renewable fuels such as hydrogen and carbon feedstocks. What we try to develop is really taking solar panels and coat them with catalytic layers so that we can make renewable fuels instead of electricity. What we are aiming for is a real-world demonstration where we can take our technologies from the laboratory into the real world and demonstrate that this chemistry, the conversion of solar energy directly into renewable fuels, is feasible.
I'm Sam Stranks. I'm a professor of optoelectronics in the Department of Chemical Engineering and Biotechnology here in Cambridge. We lead the aspects on the halide perovskites, making scalable photoabsorbers. We've used facilities right across the university. We've used facilities in chemistry for the photocatalysts. We've used facilities in the Department of Chemical Engineering and Biotechnology for some of the depositions. And we've also used facilities in the Maxwell Center in physics, where we've been using the Henry Royce Institute ambient cluster to scale up these halide perovskite materials to make the solar leaves. So we've been working together for the last 3 or 4 years. We've been working from small lab scale demonstrations and now we've recently hit a milestone of having a meter square panel that we've been able to test outside.
The first crucial step to fabricate our solar device is to make sure that the substrate is as clean as possible. In order to do so, we have a protocol to remove any kind of organic material and dust from its surface. Once we have thoroughly cleaned the substrate, we proceed to evaporate our host selective layer, which is key to ensure that the device works as it is supposed to. This layer has to be uniform, homogeneous, and free of pinholes to facilitate the further deposition of the perovskite absorber and the electron selective layers. The deposition of a high-quality, large-scale perovskite layer is essential for the success of our artificial leaf prototype. For this, we use the hybrid module of the Royce ambient cluster tool, where we have access to a vacuum deposition chamber where we can co-evaporate 4 different sources to obtain a complex perovskite alloy. This perovskite efficiently absorbs light and produces charge current, but also is very stable over time, which is very important for our purpose. After the deposition of the perovskite, we evaporate the electron selective layer and the metal contacts to close the full device.
Until now, we have seen how the light absorber is deposited, but for the purpose of our project, we also need to have a catalyst, a material that will be able to convert small molecules like water or carbon dioxide into a useful product, syngas, which is composed of hydrogen and carbon monoxide. For this purpose, we will now move to chemistry, where we will show you how you can deposit a porous copper indium catalyst onto a copper substrate. Until now, we have seen how we can prepare the light absorbers and how we can prepare the catalyst. Now, in our case, we want to make these large-scale solar panels for fuel production. So in this case, we need to assemble these different components. Here, we will assemble the catalyst with the perovskite light absorber and with the bismuth vanadate light absorber into one single panel. Now, this is only the first step of our procedure because we will also need to make a large array of these panels. And once we have these, we can actually integrate them in a reactor that can be later used for outdoor experiments.
So before we started the collaborations, we were constrained to square centimeter systems in the lab. And thanks to this project, we could scale to a square meter and really test them in the outside real-world environment. So we think that's a very important step to test the feasibility and move forward with this technology. There are many applications. So today we are used to solar panels that make electricity. With these solar panels, we could in principle produce, for example, hydrogen that can be used for a hydrogen economy. We can use them at land, we can use them at sea for heavy transport, for aviation and many other possibilities.
So we still need to keep working on efficiency of these materials. We need to work on the absorbers to make more efficient light harvesting. We need to make different fuels as well, because there's a diverse range of fuels that we could make. There's also lots of understanding we still need to do about outdoor stability tests and understanding where losses are and where instabilities come in. So we thank our funders for making this scale-up activity in particular work. So we thank the Henry Royce Institute, the Maxwell Centre here in Cambridge, the Yusuf Hamid Department of Chemistry, the Department of Chemical Engineering, Biotechnology and School of Technology, and CAMIS for the funding.